differential equation and vector calculus. Topic title: Assumption in Bernoulli's equation. My name is Firoz, my ID. The Bernoulli's equation is a fundamental principle in fluid mechanics that describes a behavior of fluid, liquid, or gas moving along a streamline. It is based on the conservation of energy principle and state that the sum of pressure energy, kinetic energy, and potential energy remains constant in an ideal, incompatible, non-viscous fluid. Derivation of Bernoulli's equation. Bernoulli's equation can be derived from the principle of conservation of energy applied to the fluid element moving along the streamline, which constantly moves in a same state. Considering the small amount of energy of fluid is density pi by rho and following the streamline, the total mechanical energy per unit volume is pressure pp, pressure exceeded per the on the fluid, kinetic energy, and potential energy. This means the fluid follows through the same system. If one energy terms increases, another must decreases to maintain the balance. Assumption in Bernoulli's equation. The equation is derived based on the following key assumptions. Steady flow. The fluid properties velocity, pressure, density do not follow the change over time. Incompatibility of flow. The fluid has constant density valid for most liquids. Non-viscous flow. The fluid has no internal interrefraction. Viscosity is negligible. Irradiation flow. Non-rational effect and the vortex exist in the flow. Following along the streamline. The equation is valid only along the single streamline. No external work or heat transfer. The system does not gain or lose energy from the external sources. Applications of Bernoulli's equation. Bernoulli's equation is widely used in various engineering and scientific fields including aerodynamics, Wernicke effect, and hydraulics. Aerodynamics explain how the airplane wings generate lift. High velocity above the wings leads to the lower pressure, and virtuous effect were used to flow the measure devices like vectometers where pressure drops indicates the flow of speed. Hydraulics helps in detaining water distribution system, pipelines, and pumps. Mechanical applications used to understand the body flow through the arteries and veins. Meteorology helps explaining wind speed and pressure variations in storms. Limitations of Bernoulli's equation. Why Bernoulli's equation is powerful to limitations. It does not apply to turbulent flows. It ignores the viscosity effects, requiring modifications in real world applications. It assumes no energy loss, which is unrealistic in practical system. To address the limitation, energy often uses modifications like Navier-Stokes equations for some modern complex fluid flow scenarios. Derivation of Bernoulli's equation. Before discussing and assumptions, it is important to understand how Bernoulli's equation is derived from. The Navier-Stokes equation by integrating the Euler's Euler's equation further injects into flow of along the streamline. The Bernoulli's equation takes the form pressure where pressure per unit volume and some of these major assumptions in the Bernoulli's equation are validity of the Bernoulli's equation depend on several fundamental assumptions which we will analyze in detail. Steady flow. The equation assumes that the flow properties velocity, pressure, and density does not change with time. Mathematically, the assumption is valid for long-term consistency of flows but fails to transit conditions like pulsation of blood flow and unsteady aerodynamics. Incompatibility flow. The fluid density remains constant through the flow. This is good assumption for liquids, but oftenly invalid for the gases and high velocities. High velocities. Example like compressed aerodynamics in supersonic jets, fractional flow neglecting the velocity. Fractional flow. The Bernoulli's equation assumes that the velocity internal fluid fraction is negligible. In real world applications, the pipe flow, boundary layers, and turbulent motion viscosity plays a major role in them. For viscous fluids like connecting using the Navier-Stokes using unnecessary the following along the streamline. The equation applies a strict along a streamline, straight streamline means different streamlines can be different Bernoulli's constants. The assumption holds the irrotational flow but not the swirling or vortex domain flows. Irrotational flow. The assumption of irrotational means the fluid does not exhibit rotational motion. In real flows, vortex, turbulence, and eddy current, eddy flows, eddy violets are assumption. This assumption. Applications such as tornado, mode running, and wingtips and vortex requires modifications to Bernoulli's equation. No external work done by the fluid. Assumption no pumps. Assume there are no pumps, turbines, or mechanical devices are added to the extracting energy. The real system devices like compressors, fans, and propellers introduced energy requires modified equations. No heat transfer. Assuming the flow is adiabatic, no heat energy is surrounded. This assumption fails thermodynamically active systems such as steam turbines or atmospheric heating. In real world applications and limitations, in aerodynamics, Bernoulli's equation will help lift generations of aircraft wings. At high speed jets, compress effect requires using the compressibility Bernoulli's equation. Hydraulics and pipe flow. The water distribution system Bernoulli's principle is applied but only for viscous loss. The Dargin-Swissbach equation is an alongside Bernoulli's equation to account for the fractional loss. Medical applications. Use it to analyze the blood flow in arteries and veins. Fails in pulsatory flow conditions requires time depend on the corrections. Meteorology. Explains the pressure difference in hurricanes and tornadoes. However, turbulent effect and temperature variations compare detect applications. Correcting for assumption violations. When real-world conditions deviate from the Bernoulli's assumption, severely modifications are required. For viscosity, Navier-Stokes, strongness, or moderate charts for compressibility. The comparability of Bernoulli's equation for unsteady flow time-dependent version of Bernoulli's principle. Conclusion. While Bernoulli's equation is a powerful tool to fluid dynamics and it capable acceptability and heavy dependence on the assumptions. Understanding these assumptions is a crucial for engineers, physicists, and research workers in the real-world fluid system. Thank you.